Hi, it's Mrs. Yake. I just want to do one piecewise defined function example with you so you have something to refer to when trying these problems tonight. First of all, let me remind you that piecewise functions are just that, functions, and therefore, in this example here, every time you plug in a number for x, you will get one and only one answer out for your output. Before we graph this, I want to evaluate this function at 0, 1, and 2. And so you need to check these inputs into, remember what we called this? A little mini domain, the little mini domains. And so if you're trying to find f of 0, you're not plugging 0 into both of these, you just have to decide which one you're plugging it into. So if you're plugging, obviously 0 is less than or equal to 1, so you're going to plug 0 in here. So f of 0 is 1. F of 1 now, because these both say 1 on them, so you need to go to the one that x is less than or equal to 1, so it fits there. So you plug 1 in there, and that gives you 0. And plugging 2 is greater than 1, so 2 squared is 4. So it's a matter of finding the correct output piece that you want to plug your inputs in. All right, so the domain is really the combination of all these little mini domains. And so if this is all x's that are less than or equal to 1, and this is all x's that are greater than 1, then that's everybody. And so the domain here is all real numbers. The range, which is your output, it's not always easy to see looking at the function, so let's graph it next and then we'll answer that question about the range. Okay, graphing just y equals 1 minus x, graphing this piece first. You can remember slope-intercept form and do it that way. This has a y-intercept of 1 and a slope of -1. But remember, all the graph is the ordered pairs, x, y, that make this a true statement. So the first piece I'm graphing is y equals 1 minus x. So if you want to play the game plot-a-lotta, that's fine. Plug in 0, you get 1. Plug in 1, you get 0. Whoops. Plug in 2, you get -1. Plug in -1, you actually get 2. And so if you remember from last year, what we did is we just very lightly sketched and said, okay, that's the function. I gotta find my eraser here. That's the function y equals 1 minus x. But I don't want all of that. So where do I need to get out my scissors? Is right here when x is less than or equal to 1. So I'm going to go over here when x is 1. This is kind of my shopping place. And when x is less than or equal to 1, so this will be a filled in circle. And then I will make this nice and dark. And I'll erase, whoops, erase that. So there is the graph, y equals 1 minus x, if x is less than or equal to 1. The second graph is y equals x squared. You all know what that looks like, but let's just plot some points. It's a parabola. Goes through 0, 0, 1, 1. Whoa, not 2, 4. Yes, 2, 4. Not 2, 2, 2, 4. -1, 1, -2, 4, and so on. So very lightly, here is our parabola. But I don't want all of that. I just want the piece where x is greater than 1. So if I go over to 1, the point 1, 1 is on the graph. I'm going to use an open circle here, because it's strictly greater than, not greater than or equal to, and then I'm going to erase that. Hey, if this was greater than or equal to 1, and this was less than or equal to 1, then this would be filled in, and this would be filled in, and then it would no longer be considered a function. It would not pass the vertical line test. All right, now looking at the picture here, the domain is all real numbers, because if you squish that graph, my hands on here, if you squish that against the x-axis, it covers up the whole x-axis. But if you squish it against the y-axis, the only kind of numbers that you are going to get out for your outputs are all real numbers, these are your y values, greater than or equal to 0. Another way of saying that is all y such that y is greater than or equal to 0. Another way of saying that with interval notation is from 0 to infinity, closed bracket. Okay? See you tomorrow.